downside is that the commercial agencies don't care about the science. They care about making money on the launch. Now, they may be able to charge a government, US government, European government, a fee for launching a spacecraft, and that business plan, I don't think it'll make a lot of money, but it might do. So the plus side is that you have more launch capability, plus there's a commercial interest in designing a better launch capability. They have all the money to invest in it that the government probably doesn't have. So that's the positive. The negative is, of course, that ultimately you want to fly your mission, somebody comes along and says, I want to fly, this big Coke ad or something. The money talks, and so that could ultimately affect the science and those kinds of decisions. Plus, you may have to modify the science you do in order to build a spacecraft that's this shape rather than that shape because of the adaptability. So there's a lot of issues, but overall I think it's very positive just to get you into space.
One commercial flight I'm a consultant on right now is a solar wind monitor, and we have an interesting dichotomy between research missions that are NASA's purview and monitoring missions, which is NOAA's purview. So all the weather monitoring satellites, for example, are run out of NOAA. Up till now, all the solar wind and solar monitoring missions, because their research have been run out of NASA, but they're in the process of transitioning. We really need to know what the solar wind is going to be because of space weather effects on astronauts or commercial hardware in space. And so we have a spacecraft at L1 right now called ACE, and it's beyond its design lifetime. And if it died tomorrow, it wouldn't be a failure, but we would be really in deep doo-doo. So what NOAA has agreed to do, NOAA doesn't want to fly it. I mean, so it's in this no man's land between NOAA and NASA. But NOAA has agreed to buy the data. So they're looking for commercial partners that will fly the spacecraft and sell the data. And the idea is there will be a guaranteed data buy, which will cover the cost of the spacecraft. And so now that commercial partner is now looking for additional customers for the data, so they can make a profit. So it may have Coca-Cola on the side, who knows? But those kinds of issues, when you have a commercial partner, there's some advantages and disadvantages. I think one of the biggest advantages of commercial partner is that they can take a little more risk. I think commercial partners can try a little more advanced technologies because they've already got investors that are prepared to take some risk. The other thing is in the manned missions, I mean, they can take private people up in space, which NASA is kind of, is not in a position that they want to do, but it's actually a way to make money in space is to take up rich people. or musicians, or somebody famous, or sell ads, and none of that NASA can do, but a commercial entity could do. So I think those are kind of the pluses. The minuses is, of course, it may be more expensive to have a commercial launch vehicle unless you can, do some of these piggyback things. So there's definitely pluses and minuses, but I think the risk is one huge issue. As David mentioned, NASA's become very risk averse. Well, when we had a new NASA administrator, Dan Golden, a few years ago, he came out with faster, cheaper, better. And here everybody says faster, cheaper, better, pick two. But the idea is if you've got an unmanned mission that's 99% successful, predicted, it's 10 times as expensive as one that's 90% successful, predicted. Okay? The rule of thumb is every additional 9 in reliability is a factor of 10 in price. So Golden said, hey, let's drop the reliability down to 90% from 99 and fly 10 missions instead of one, and bear in mind that one of them's going to fail. But we're going to get 9 times as much data back because we will have taken on some acceptable risk. So he proceeded down this path and flew a bunch of missions, and 20 missions went up and 2 of them failed, which was exactly what he predicted. And then everybody went up in arms, oh my God, you've had all these failures. We're going, this is what we plan to do, folks. So I think even when NASA deliberately tried to take on more risk, it backfired on them. So I think commercial companies can get away with that. Now, if you're flying people, 90% is not good enough. 99% is not good enough. We'd like to see, 99.9, and that's when the price for doing business gets really, really high.
So what do you guys think about possible missions to asteroids and to Lagrange points? And just going back to the moon in general, what kind of science can be done that's either better if you're on the moon, or is it just geological science, or is there more that you can do from the specific location?
Well, I don't know, just exactly. Personally, I have not looked at the details of this, but I have heard reports, read some reports that suggest, at least for astrophysics type missions, having a relatively stable platform on the moon could let you do more ambitious things in terms of telescopes to study astrophysics. But there is the issue of getting things there and getting things back. So I don't know that it will truly be cost effective in that sense, but you could imagine doing some things from a moon base that I don't think you would really consider doing just in orbit. But we are sending missions to the Lagrange points. JWST is going to go out to one of those Lagrange points. The Next Generation Space Telescope. It's JWST. It's a James Webb Space Telescope. It's the first, I believe it's the first mission NASA has ever named before it's actually gone off the ground, because they kind of don't want things that have names blowing up on the launch pad. But this one has a name, and not after a scientist.
So what's the benefit of being in the Lagrange point as opposed to just orbit?
The Hubble, I think the Hubble has been a grand success in pretty much any way you can measure it. But because it's in a low orbit, so that the shuttle can service it, the Earth gets in the way every time it goes around. And so it causes problems for continuous observing. It also goes through, you have to worry about anomalies of the Earth's magnetosphere affecting things up. You can get away from all that when you're at the launch points.
The other thing for Hubble too is because it's going to be looking further back, everything's not everything, but most of the optical stuff is redshifted into the infrared, so it has to be a really cold telescope. So by being able to look out into space, you can get down to like 10 or 20 Kelvin right away without doing anything in terms of cryogenics on the spacecraft. So the L2 point helps you provide a stable platform away from just heat coming off the Earth and things like that. So it helps provide that as well. We have a mission right now called Stereo that's working its way to essentially L5, and we talked about an L4, which I've got my numbers right. L3 for far-side observers. The advantage, we have a whole bunch of spacecraft bases at the L1 point. The Soho spacecraft is at the L1 point. Something else there too. And it provides essentially, it's not quite stable, but an equilibrium point. For operational solar physics or operational heliophysics, what it does is it sits in the path of anything coming from the sun to the Earth. And so you can measure magnetic fields at that location, you can measure particle flux densities, energy spectra, the whole works, speeds, solar wind speeds and everything. And that gives you a certain amount of warning for when, say, a coronal mass ejection is going to hit the Earth. The fastest coronal mass ejections, once they pass the L1 point, take about half an hour to get here, so it's not much of a warning. But it does provide real measurements that you can't really get remotely. When you look at the sun, that this coronal mass ejection waves takes the fastest ones take a day to get here, but you don't know if it's going to have a geo-effectiveness because it may not have the right field orientation, a whole bunch of things. So having something there provides let's see if I can pronounce it Americanly, a buoy, a buoy at that location that actually makes the measurement. We have talked about sub-Lagrangian points using solar sails, but if you get me on solar sails, I'll be here longer than I usually am.